reason why I had to put a question mark here was because I don't really think there are that many dummies here today. But I will try to give I'll start to just tell you a little bit about the Nordic power system and hydropower, and then the basics behind production planning, some common simplifications that we use, and the different type of modeling tools. Now you've already seen how, like, the process going from water to energy, and we've heard about the turbine and some limitations and possibilities we see in the turbine design, and we've also heard about the environmental design. And all of these things are elements that we have to consider when we plan production, or when we do production planning. So I think you'll understand more now than if you didn't hear all of that before my talk. So the Nordic power system, so the Nordic region, Norway, Sweden, Denmark, Finland, and also this Eastern Europe countries here. In this region, we have a mixture of different kind of energy sources, and it's a liberalized market, and the market is also connected to the rest of Europe. So it's we are also affected about what's happening in Europe, but the special part about the Nordic system is that hydropower accounts for about 50% of the capacity, which is quite unique, and it's we're very lucky to put it in that sense. But it's quite complex. It's a huge system with more than 1,000 reservoirs, and it's also related to uncertainty because we have this inflow, which is inflow of water into the system, and it varies a lot. So we can have a wet year or a dry year, and it really affects, at the end of the day, it's how much energy do we have available. And we don't know that when we start off. And then we have some important trends. We have, there are a lot of work on interconnectors to Europe. We'll be more close or stronger connected to Europe, so what happens in the rest of Europe will affect us more. Europe is going through a transition to a low carbon system, which means more intermittent energy production. That is a challenge for the system, but it's also an opportunity, especially because hydropower has a great potential of balancing out these imbalances of the unpredictable and uncontrollable energy sources. So what is special about hydropower? Well, we have a marginal cost approximately equals 0. We don't have a fuel cost, at least. And we have no emissions, and it's renewable, it's flexible, and it's controllable. So it's perfect, right? Well, it is very, very good, but we are dependent on the available water. So there is it's stochastic. It means that we have uncertainty. And we have, it's a dynamic problem. It's dependent, what I do today will affect what I can do tomorrow. So there are dependencies in time, so between different time periods, which makes it more complicated to make an optimal strategy. So just production planning. What are we trying to do? Well, we're trying to optimize how we use the water we have available. And when I say that we try to optimize the production, that means we try to minimize the socioeconomic cost for our society, or maximize the social welfare. From a producer point of view, that means giving a perfect competition assumption. That means that the producer tries to maximize profit. But when we look at it from a fundamental point of view in our model, that means to minimize the socio-economic cost. Produce at high price and high efficiency, but also consider your reservoir and the level in your reservoir. So we already talked a little bit about this, right? You have a maximum level and a minimum level. And we We want to avoid flooding or spillage, because that's lost value. And we want to ensure that we have available water, because we don't want to end up in a situation where we have rationing or curtailment. And also, if you don't have any water, you don't have any options. You don't have any cards to play, right? So the main uncertainties are inflow and price. And we talk a lot about water value. And that's because we need, so I can produce today and I will get a price, right? But what's the value of storing the water? And that's why we talk about water value and why we calculate a water value. That's the value of waiting, of storing it and using it for another time, in a later period. So first, if you look at uncertainty in price, I can use the water now, and then in the next period, I will get some new information. And it could be that in the next period we have a high price or a low price. But if there's a low price, then it's a good thing that I already used it, assuming that I had a higher price before. And similarly, I can store it, but then if I store it and I get a low price, then that's not going to give me that much value. And if I store it and have a high price, then I'm very happy. But then I also have to consider my reservoir level. So I can use water, meaning that I will have a lower level in my reservoir, which is great if there is a high inflow later, because then I still have room for that water in my reservoir. But it's not that good if it's not that much inflow, because I might end up with curtailment. Similarly, if I store the water, that's good if there is low inflow, because I still have water to spend, but it's not that good if we have high inflow, because I might end up with a situation of spillage, which is lost value. So it's simple enough. The main idea is quite simple. So why is it not so simple? Well, we have, like I already mentioned, it's a dynamic problem, so it's coupled in time. And often we have long time horizons, because some of these reservoirs can store water for a long time. So we need to consider sometimes years ahead. Other times you can only consider like the next week. It kind of depends a bit on the scope of what you're doing. We have a lot of uncertainty. There are several uncertain parameters, and we have to choose to what degree we include this uncertainty in our problem. And these problems are large. So we already saw just this description of one plant, from one reservoir to one production unit. And this is one river chain and one system of connected reservoirs with different kind of intakes and several plants or production units. And then there are several of these. So it's quite complex, and imagine like what you decide to produce here is going to affect what you can produce here, right? So everything is connected, and that makes it even harder. And this problem, it grows to be enormous quite quickly. It becomes so large that it's difficult to handle it computationally. So we have to do different simplifications, and these are some of the most normal simplifications we do. So we talk about the spatial dimension, and it's the physical dimension. It could be like geographically, or the number of plants in your system. Like, it's the physical size of your system. And we can simplify this by, we can limit the system. We can say that, okay, we're just going to look at this one river chain. And then we have to represent the rest of the world with some kind of price that this system interacts with. So that makes it a lot smaller. Another way is to say that, okay, but we need to consider this large region, but instead of representing every power plant, we will aggregate it and say that there is just like one big reservoir in Norway with one big plant. So you lose a lot of details, but it's a way, if you want to look at a really big region, let's say you wanted to look at the whole world, then that might be a necessary simplification. Then the temporal dimension, that's time. So you can have a long time horizon, and the longer the time horizon you have, of course, the bigger is your problem. But you also have the resolution. So do I divide my periods into a quarter, half an hour, a week? It depends on what I am looking at. What do I want to investigate in this? Or what am I going to use my model for? And then, especially if you have uncertainty, then for every period, you might have new information added to your problem, meaning that this is a new decision stage. And if that's the situation, then the problem just really quickly grows. And then you have technical details. And this is why I'm so glad we already had other presentations, because we try to describe the actual system, the real world, how it looks. But that's not always easy, and you've seen that there's a lot of different elements, and we need to choose what to take into our modeling and what to not include in our modeling. And then it's important to know which kind of capabilities or limitations that are the most important ones. So we have technical restrictions such as start and stop and ramping that you mentioned. But we also have environmental restrictions that are not physical limitations, but limitations we put on our system because we want to preserve something. And also another modeling perspective is, are these going to be time dependent? Are they going to depend on the different nodes in your system? Which again means that it gets even more complex. And again, uncertainty. Uncertainty always makes it more complex. So, so this is all about how we model the production part, right? But then in production planning, we also consider the rest of the market. But I will talk more about that part later today. So we'll stick to the modeling of the system and the description of the production system today, or in this part. So this is just an example of how you could use a finer, more detailed description in your modeling, but you could also aggregate it up to a quite simple description. Yeah, so as you might already kind of have understood a little bit, is that we have different type of models for production planning because we do different kind of simplifications. So we could look at a large region like the Nordic region, and we can have a fundamental market model. That means that we have a market clearing, so we model the demand side and we model the production side, and they need to balance out. And that could give a price forecast, and it can look at a long time horizon. And it's not going to be a good model to model like your production for every single hour of the day, but it's a good starting point when you look at a large system. Then we can look at individual water chains. And we're still in the long-term planning or seasonal planning perspective, but it's a much more limited system, and it needs to take some price, a power price, as input to describe what's happening around that system. And then if we shorten down the time horizon as well, then we are at the short-term planning, and we can have, so we have a small system and we have a short time frame. So the problem is much smaller, which allows us to include more technical details. So these models could be, are very good for everyday use. And they can take in details like, I have problems with a tunnel or a intake, or like very system-specific details, which would be like impossible to include in your fundamental market model because it gets too large. So to sum up or conclude in a way, production planning is quite complex because there are so many things that you need to consider. But what's really important is that you need to prioritize what you consider and when you consider the different things. So you need to know your problem, you need to know what you're trying to model and what you should use this model for. And then you need to know your assumptions, which assumptions are, what am I including in my modeling, but also what am I excluding? What am I, like if I can say, no, I'm not going to include ramping restrictions. But then you need to know, okay, that has a consequence on the results. So because you make these assumptions, you should also look at sensitivities, or try to find a way to look at how the different restrictions you use affect your results. And yeah, so it's possible, but you need to understand what you're doing. Yeah. Thank you.